Hello everyone, and welcome back to this series on the foundations of mathematics. Today we're going to be focused on a concept known as summation notation. Some people will also call it sigma notation, which is a very easy way to compactify the representation and notation of the sum, or the representation of the sum, of several objects at once. So let's introduce just a couple basic things that you might remember from grade school mathematics. The first topic that I want to mention is what is called an arithmetic sequence. So what exactly is an arithmetic sequence? So let's assume that we have an initial term of the sequence. Let's call it 7. And let's assume that the next term of this sequence is 12. So obviously, how do you get from 7 to 12 in a basic arithmetic way? Well, obviously, you would just add 5. So if this is the start of an arithmetic sequence, then the next term will also have a difference of 5. So obviously, 12 plus 5 will generate a new term of 17, followed by 22, followed by 27, and this sequence can continue onwards down to, for example, 1562. It could also be 1567 because, in case you cannot see, the last digit is either 7 or 2, as long as we keep that difference fixed, right? So that's plus 5, and that's going to continue with plus 5. Some people will also refer to this 5 as D, and some people will call this the common difference of the arithmetic sequence. Now, there are several different fun properties about arithmetic sequences one can discuss, but I'm actually going to segue this into the next topic. So on top of arithmetic sequences is a topic known as arithmetic series. So both starts with the word arithmetic. So what is the difference? So the arithmetic sequence is simply the sum of an arithmetic sequence. Great. So if that is the case, if we continue using the same exact example, the arithmetic sequence is the sum, and I'm going to be representing that sum as fancy letter S. So the sum of that arithmetic sequence is called an arithmetic series. So this is going to be 7 plus 12 plus 17 plus 22 plus 27, all the way down to, let's assume we stop at 1562 again. So this obviously is the first term of the series, which I'm going to call A0, which is technically also the first term of the arithmetic sequence. This is the second term, so I'm going to call it A1, and then A2, and that's going to be A3, and that's going to be A4, and I'm going to continue this all the way down to AN. Right? So AN is sometimes referred to as the terminating point of the sequence and or the last term of the series. Right? So how can we represent this in a more nicer way? So if I have introduced the notation 1, 2, 3, 4, and down to AN, and some people might actually also call this A0, or the initial term. Some people call it A0, the initial term, instead of A1. So if that's A0, then that means that is A1, that is A2, and that is A3. And some people will still refer to this as AN as the terminating point. The only difference is just a shift by 1. But if we take this blue convention as instead of the orange convention, then what we have here is that S can also be represented in a more compact form as A0 plus A1 plus A2 all the way down to, say, AN. Now, a more compactified version is the following. So obviously there's this number here, sometimes referred to as the index of the expression, and that is incrementing from 0 all the way down to m. So if we create a new indexing variable, and some people will change this letter. Some people will use K, some people will use J, some people will use I, some people will use N, but we're already using N, so we definitely can't use N here. But technically K will be equal to 0, 1, 2, 3, all the way down to n. So technically we can say, okay, s is just going to be equal to a when k is equal to 1, or ak when k is equal to 1. And then this is going to be ak when k is equal to 2, ak when k is equal to 3, all the way down to ak when k is equal to n. And of course, keep in mind, sometimes we do start this series instead of at 1. Sometimes we start it at k is equal to 0. Just make sure that you're consistent with your notation, or make sure that you're paying attention to the range of your indexing variable, because obviously we see that k ranges from 0 all the way up to n. All right, so that's the range of our indexing variable. So that means I can write this in another way maybe. So s is just going to be the sum. So that's where this fancy sigma, that's capital letter sigma in Greek, notation enters the conversation. So the first thing you need to say is, okay, what is your indexing variable? I'm going to choose k, and k is going to range from 0 to n. So 0 on the bottom is your lower limit, n is your upper limit, so you're going from 0 to n. I guess technically you could write k is equal to n on the upper bound, but most of the time people don't write that, so we're just going to keep it in the traditional form. So all we're going to do is we're just going to be summing the values of ak. Right? So this is the common way of representing an arithmetic series. Right? So this is the arithmetic series. And usually we can say that this is in summation or sigma notation. Summation or sigma notation. Okay? So if that is the case, can we make n bigger? Obviously that is possible. For example, maybe we can say that s is equal to a5. We don't have to start at a0 if we don't want to. We can go to a6, we can go to a7, we can go to a8, and we can go all the way up to a999, and we can technically go on forever. So if you see ellipses points that don't really have an n, this is pretty much saying we go on forever. Forever and ever and ever and ever. So if you have 1 point, there's always going to be 1 point that follows. So if this is the case, obviously k is going to range to 5, k is going to be ranging to 6, eventually k is going to hit 999, and k is going to go to what we call positive infinity. It's just going to go on forever. So if this is the arithmetic series that we're dealing with, then we can write this in summation notation as well as the sum from k is equal to 5 to infinity of ak. Right? So that's just a quick outline of the notation. So let's actually go backwards and see if we can go from summation notation to actually the arithmetic form of that. So let's just go with a very basic example. So example 1. Let's assume that we have the sum from k is equal to 5 to 9 of k. So what is this going to be? So keep in mind, k is going to range from 5 to 9. So that means this summation, since we're just evaluating k, this is just going to be equal to 5, then 6, then 7, then 8, then finally 9. And once you find that sum, that will be the value of that arithmetic series. Okay? So let's just make another quick example. So suppose we have the sum from k is equal to 2 to 7 of k squared. So now we're going to plug in the values of k, then square them, and then add up those square values. So the very first value of k is going to be 2, so we're going to have 2 squared, and then we're going to go to 3 squared, then we're going to go to 4 squared, then we're going to 5 squared, all the way down to the last term, which is going to be equal to 7 squared. Right? And let's do another example. For example, suppose we have the sum from k is equal to 5 to, let's go to 100, let's say. Let's do something a little bit more crazier. Let's do 1 over k to the power of k plus 1. So you might want to take a moment, pause the video, and see if you can give me what this would be equal to. So what is this going to be? So k is going to start at 5, so we're going to go at 1 over 5 to the power of 5 plus 1, which is going to be 6. And then the next value would be 6, so it's going to be 1 over 6 to the power of 7. Then 1 over 7 to the power of 8. And that's going to continue all the way down to, so the last value that k is going to be 100. So this would be 1 over 100 to the power of 100 plus 1, which is going to be 101. And then it would just evaluate what that sum would be, and that would be the value of that particular term. Right? Now, another very important one that I do want to mention is, and I'm going to just focus on this a little bit more, is the sum from k is equal to 1 to n of just k. So this is obviously just a special case of an earlier example, or more so a general case. And this is just going to be equal to what? So this is just going to be equal to 1 plus 2 plus 3 all the way down to m. Right? So this is obviously an arithmetic series with a common difference of d is equal to 1. So one could ask, is there a fast way of figuring out what exactly is this sum equal to? So if I give you a value of n, will you really do 1 plus 2 plus 3 all the way down to 5 million one by one? Or is there a formula for which you can just plug in the value of n and then you get your answer? The answer for this particular problem is yes. So how are we going to find it? So there's very many different artistic ways of finding these arithmetic sums, but I will show you a very common way for this particular problem. So let's look at our sum s, which is obviously equal to 1 plus 2 plus 3 all the way down to m minus 1. That's the penultimate term. And then finally the last term, which is going to be m. Now, I also want to look at this sum because keep in mind, addition is commutative in the set of real numbers. So I can add these backwards if I want. So instead of starting from 1 going up to n, I can start at n and go down to 1. So the first value I could do is n, and then I could do m minus 1, and then m minus 2. And that's going to continue all the way down to 2, and finally 1. All right? So notice that these must be the same value. Right? So for example, both could be equal to 50, right? So if that is the case, then I should also be able to add these particular expressions together. Because if s is a number and s is a number, then I should be able to add s up. So what is s plus s? So s plus s is obviously going to be equal to 2s. And then I'm going to add these, and these. Now, there's something beautiful about the setup, and what do you see? So what is 1 plus n? Well, that's obviously going to be equal to m plus 1. What is n minus 1 plus 2? Well, that's also equal to m plus 1. What is m minus 2 plus 3? That's also equal to m plus 1. And then we're going to continue all the way down to n minus 2 plus 2. That's going to be m plus 1 again. And then finally n plus 1, and that's just m plus 1. And keep in mind, in this particular expression, there are n terms. 1, 2, 3, 4, down to m. So if that is the case, that means that 2 times s is just going to be equal to m plus 1 times n, because we're adding itself to itself n times. Right? So we have that 2s is equal to n plus 1 times n. So we can just divide both sides by 2, and we see that s is equal to n. I'm just going to rearrange this. N times n plus 1 over 2. Right? So that means, in conclusion, if you have 1 plus 2 plus 3 all the way down to n, this is just, in summation form, the sum from k is equal to 1 to n of k. This is just going to be equal to n times m plus 1 over 2. Right? And this is a very important sum that has several different applications, which we'll discuss at a later time. To review what we just learned, suppose somebody asks you, what is 1 plus 2 plus 3 all the way down to 82? Obviously, we can clearly see that this is an arithmetic sequence, or an arithmetic series, with common difference plus 1. So we can clearly write this as the sum from k is equal to 1 to 82 of k. We've already derived the formula for this. Since n is equal to 82, it's just going to be n times n plus 1 over 2. So that means this is going to be equal to 82 times n plus 1, which is going to be 83, all divided by 2. And one should be able to show that that's equal to 3403. So if you were to do this one by one, this is the value that you will get. Now, what I want to do is I want to go back to the previous arithmetic series, which was, I'm going to call S, to be equal to 7 plus 12 plus 17 plus 22, and instead of going up to a large number, I'm just going to go up to 57, just in case you want to verify this on your own. So is there a fast way of figuring out what this sum is equal to? And again, notice that the common difference for this particular arithmetic series is 5, right? So the first thing that I want you to notice is that I can represent 12 as 7 plus 5, right? And you can represent 17 as 7 plus 10. And you can write 22 as 7 plus 15. That is, I'm writing this in terms of the initial term and a multiple of the common difference. So let's take a closer look at what that would look like. So that means this is going to be 7 plus 5 times 0. So that's going to be equal to the first term. And then plus 7 plus 5 times 1. That's going to be equal to the second term. And then what is 17? Well, 17 is 7 plus 5 times 2. And then we have 22 to be 7 plus, take a guess, 5 times 3. And then we go all the way down to the last term, which is going to be equal to what? So plus all the way down to 7 plus 5 times. So 7 plus what gives you 57? That's obviously going to be 50. And 50 is equal to 5 times something, and that's obviously going to be equal to 10. This 10 is a very important number because that corresponds to the n value that we're looking at. Because look at here, that's going to be k is equal to 0. That's k is equal to 1. That's k is equal to 2. That's k is equal to 3. And that obviously is k is equal to 10. Right? Now, keep in mind, if this is not obvious to you, take a moment, do a different arithmetic series, and see if you can figure out this particular decomposition, because this is a very, very beautiful setup. And how many terms do we have? Notice that we have 11 terms. We have 1, 2, 3 down to 10 and 0, right? That's the plus 1 at the very end. Okay, so now what I want to do is I just want to regroup this expression very quickly, because notice that I have a 7 here, a 7 here, a 7 here, a 7 here, and a 7 here. And how many 7s do I have? I have 11 of them. So that means this expression s is just going to be equal to, I'm just going to write it out here, so 7 plus 7 plus 7, all the way down to 7. And then what do I have left? Well, I have 5, 0, 5, 1, 5, 2, 5, 3, all the way down to 5, 10. So each of them are going to have a product of 5, so I can factor those 5s out. So that's going to be left with 5 times, and what am I going to be left with? 0 plus 1 plus 2 plus 3 plus 4, all the way down to 10. You see what's building here? I hope so. All right, so how many, again, 7s do I have here? I have 11 of them. And what do I have here? Oh, that's another arithmetic series, and that is the common difference in front of it. Isn't that very interesting? Right? So what do I have? So that I have s is equal to 7 times 11. That's the n value that we figured out. And then we have 5 times the sum from 0 to 10 is the same as the sum from 1 to 10. So that's 10 times 10 plus 1 over 2. So I can write that as 10 times 10 plus 1 over 2. That's that little arithmetic series value that we built. So what is this? So that's going to be 10 divided by 2. So 10 divided by 2, that's going to be 5. 5 times 5 is 25, and 25 times 11 will be 275. We have a 77 there. So that means this is going to come out to 77 plus 275 with a final value of 352. Right? Isn't that beautiful? So combining these results in a very clever way in generalizing, if you could, you should be able to show that if you have a1 plus a2 all the way down to an, and let's assume that you have a common difference of plus d, which we can write as the sum from k is equal to 1 to n of ak, one can show and prove, and I'll leave this for you advanced students, that this is just going to be n over 2 times a1 plus an. Right? So this is a very beautiful way of figuring out what that arithmetic series is equal to. The only potential challenging part you would have to figure out is what n is. Because you know what a1 is, you know what an is, the last term. You just need to figure out exactly what is n, and usually a bit of division and rounding and remainders can solve that if you know long division. Right? But of course, does this formula work for what we have? The answer is yes. Because what was n in our case? Well, let's assume that we don't know. So let's assume we have n over 2. The first term that we had was 7, and the last term that we had was 57. And what is that? So 7 plus 57 divided by 2, that's going to be equal to 32 times n. And using some algebra, we were able to figure out that the number of terms that we had in the expression was 11. So that's going to be 32 times 11, which is going to be equal to 352, which is the same value that we have earlier via manual calculations, right? So in case you can't remember that formula, or if that formula doesn't really vibe with you, you could always go back to the original factorization way, and it will always work for arithmetic series, which is very beautiful. Now that we've discussed some of the basics of arithmetic series and sort of how they fit into the summation notation expressions, now we're going to focus on a different types of series, which is called a geometric series. So a geometric series, instead of having a common difference, what it's going to have is called a common ratio. So what this is going to look like, it's going to look like a, which is just going to be a constant, plus a times r, and then a times r squared, and then a times r cubed, all the way down to, let's say, a times rn, and it could potentially go to arn plus 1 and go out to infinity, possibly. Please note that there is a 1 in front of this a, and you can technically write that as r to the power of 0. As long as r is not equal to 0, which some people will say is equal to 1, but technically not really, then this expression still will hold. And again, this r is referred to as the common ratio. Okay, now it's very easy to see that a is a common term in this expression, so some people will not define a geometric series in terms of this constant a, because we can always write that s is going to be equal to a times 1 plus r squared plus r cubed plus all the way down to something, right? And technically speaking, this could go all the way down to rn, or it could go down to r infinity, depending on if you're working with a finite or an infinite geometric series. Okay, so in this expression, the only real interesting thing to figure out is what exactly is this expression equal to if it happens to be equal to anything nice at all. Before I get into the statement of this very nice formula, I just want to recall something very basic from back in the day when we learned about factoring. So the first thing that you should remember is if we have 1 minus x squared divided by 1 minus x, that numerator 1 minus x squared is just a difference of perfect squares. So that's just going to be 1 minus x times 1 plus x all over 1 minus x. And as you notice, this 1 minus x does cancel, and then we're just left with 1 plus x in the very end. Right? Nothing scary at all, but keep in mind I can write that as x to the power of 0 plus x to the power of 1. That's the formation of it that might be useful here. Let's look at another expression that you should know. 1 minus x cubed. Let's stay consistent with colors, shall we? So 1 minus x cubed all over 1 minus x. So that's a difference of cubes, and you might remember how to factor that. That's just going to be 1 minus x times 1, change the sign. If it was minus, go to a plus. If it was plus, go to a minus. 1 plus x, and then always plus x squared, all over 1 minus x. As you can see, these 1 minus x's do cancel, and we're just left with 1 plus x squared, which, as you can clearly see, is just going to be equal to x to the power of 0 plus x to the power of 1 plus x to the power of 2. Do you see a pattern? You should, because if I were to go up another one, so if I have 1 minus x to the power of 4 over 1 minus x, then you probably can guess this is just going to be equal to x to the power of 0, x to the power of 1, x to the power of 2, plus x to the power of 3. And you should be able to verify that on your own via some basic calculations and factoring. So if this is the case, then if I multiply both sides of this expression by 1 minus x, then what you have here is that this expression is equal to the product of these two terms. So in the general case, 1 minus x times 1 plus x squared all the way down to x to the power of m will be equal to 1 minus x to the power of n plus 1. If you were to factor that, distribute that in combine like terms, you will get this particular expression. Right? And of course, I can rearrange this if I want. So this is one formulation that would be useful to you. And in particular, 1 plus x squared plus all the way down to x to the power of m. I have a double plus sign there. What is that doing there? Then this is just going to be equal to 1 minus x to the power of m plus 1 all over 1 minus x. Because what is this on the left-hand side? That is just a geometric series. So I can write that in summation form to make it a little bit more nice. So that's just going to be the sum from k is equal to 0 to n of x to the power of k. And that's obviously going to be equal to 1 minus x to the m plus 1 all over 1 minus x. Right? So that's obviously the very beautiful statement. And here x is the common ratio of this particular geometric series. Okay? Now it's very important because some people will vary this just a tad bit, and that's the lower bound of this expression is 0. Some people will start geometric series at 1 instead. So what would that exactly look like if it were to start at 1? So if you were to start at 1, so k is equal to 1 to n of x to the power of k. So this would start, instead of at 1, it would start at x to the power of 1, and then x to the power of 2, and then x to the power of 3, all the way down to x to the power of m. And this is the same thing as 1 plus x squared all the way down to x to the power of n, except that 1 is removed, right? The reason I sort of add 1 and subtract 1 is because we already know what this expression in parentheses is equal to, because that's just going to be equal to 1 minus x to the m plus 1 all over 1 minus x. And then we have this minus 1 here, which we can technically put over 1, get a common denominator of 1 minus x, and write this instead as 1 minus x over 1 minus x, right? Because that's equal to 1. So if that is the case, we can distribute this minus sign, change that 1 to a negative, the x to a positive, and then we're just going to have what? So we're just going to have 1 minus x to the power of m plus 1 minus 1 plus x all over 1 minus x. Notice that these 1's do cancel there, which is actually pretty nice. Our x is positive. We can shift him in front, and we can have that this is going to be equal to x minus x to the m plus 1 all over 1 minus x. And that's the sum from k is equal to 1 to n of x to the power of k. Right? Some people will factor out an x out of this numerator and write that as x times 1 minus x to the power of n all over 1 minus x. In short, there's no big advantage here, but sometimes that will be a little bit more advantageous to work with, right? So that's just another way of representing this geometric series in case it starts at 1 and not 0. So definitely make sure you pay attention to the limits of your summations. Now, another question, what if n goes to infinity? What if? So instead of a finite geometric series, what if you have an infinite geometric series? Right? So just a couple of, observations you could say. If x is a number between minus 1 and 1, so it's a fraction like 1/4, 1/5, 2/7, so the denominator at the bottom is bigger than the top, then you should be able to verify that if you exponentiate that term to some power and send n to infinity, it's going to get closer and closer to 0. right? For example, if you take 1 over 5 to the power of n, that's going to be 1 to the n over 5 to the n, which is just 1 over 5 to the n. As n gets big, 5 to the n gets extremely big, and 1 over something extremely big eventually will go to 0, right? But technically speaking, as long as x is between minus 1 and 1, you will still get this particular type of behavior. So if that is the case, keep in mind that the sum from k is equal to 0 to n, the finite geometric series, is equal to 1 minus x to the power of n plus 1 all over 1 minus x. So if n goes to infinity and x belongs to minus 1 to 1, then this term will vanish, right? So we can generalize this, or I guess take a baby subset of this, and say that the sum from k is equal to 0 to infinity of x to the power of k is equal to just 1 minus 0, which is 1 all over 1 minus x. But keep in mind, this is only true provided that x belongs to minus 1 to 1. If it doesn't belong to that particular interval for that common ratio, then this series is what we call divergent. Okay, and keep in mind, this is for k is equal to 0. It's possible that that series does start at k is equal to 1. So if that is the case, then what are we going to have? So we're just going to have the sum from k is equal to 1 to infinity of x to the power of k, which is just the same thing as 1 over 1 minus x, except for 1, which is just minus 1 over 1 minus x over 1 minus x, right? So we're just missing that one term. And then once we distribute, what are we going to have? We're going to have 1 minus 1 plus x all over 1 minus x. We see that our 1's do cancel, so we get the final result that the sum from k is equal to 1 to infinity, the infinite geometric series with common ratio x, is just going to be equal to x over 1 minus x. And again, keep in mind that this is only true if x belongs to the interval, open interval, minus 1 to 1. Right? So that's your infinite geometric series where the index starts at 1, not 0. There's so many applications that one could do with these arithmetic sequences and series, whether it be engineering or finance or economics or biology, but we'll get into those at a later time. I hope you enjoyed this video, and I'll see you in the next one. Take care.